Hey guys, so if you watched the optional videos on set theory, it was just a review. You might have noticed it ended quite abruptly. Well, there was another class that needed to come in and use Mod 52 to take their final, so I had to cut off the video at the end. Another thing you might be noticing about these videos is the angles keep changing, and I'm actually changing rooms. I'm trying to minimize the glare on the whiteboard, so in video 2, it seems that there was a big triangle, which comes from those triangular-shaped windows around campus, that might have cut off some of the whiteboard. I hope it wasn't too distracting, and I think I don't have it going on right now in this video. So this is going to be the first video where we actually get to probability theory. I am going to review just a bit about sets that wasn't in the set theory videos, and that we're going to use right away today. So omega, if you didn't watch the optional videos, is our universal set. This is just standard notation in probability theory. So in discrete math, I used a U, a capital U for the universal set. But in probability theory, it's standard to use omega. And another thing we didn't talk about yet in review, although we should know it from discrete math or from another class, is the power set. So the power set is a script P, like a cursive P, of a set A, and it's all subsets of A. So it's actually the set of all subsets of A. For example, if A was the set 1, 2, 3, then the power set of A would be a set containing every possible subset. So for example, the set 1 as a subset of A, so is 2 and 3. And then any two elements there also. So the set 1 and 2, the set 1 and 3, and the set 2, 3 are all subsets of A. And of course, A is a subset of itself. And then there's one more set that we haven't gotten in the collection. So this is all possible subsets, except for the set that doesn't contain anything at all. And remember, that's the empty set, which we denote like this. So the empty set just doesn't have anything in it. It's not nothing, but it's the set that contains nothing. So it is something, it's a set, but it just has no elements in it. So every subset of A is listed here in the power set, and that's what the power set is. So now we'll let omega be any set. A probability is a function P. That's not a script P, that's just a regular capital P, which maps from the power set. So here's our script P of omega to the interval 0, 1, such that two things are satisfied. So first of all, P of omega, if we plug in this whole set, so this is all subsets. You can put in any subset into P, but if we put in the entire universe, we map to 1. So remember, this goes from 0 included to 1 included. And this is just the real interval, the real numbers from 0 to 1. P of the entire universe has to be 1. And 2, if A1, A2, and so on are sets such that A sub I intersect AJ equals the empty set. If I does not equal j, then the probability of the union from n equals 1 to infinity of AI is the sum from I equals 1 to infinity of the probabilities of the AI. So that's the definition of probability. That's the main the main thing we're studying in this class. I should back up and be a little careful about a few things. So we're saying that P maps from the power set, in other words, all subsets of omega from 0 to 1. That's going to be okay for this class. We don't need something more complicated than that. But if you were to take a more advanced class in probability, you'd have to be a little more careful. So in general, whenever we're talking about like the real numbers or something, we don't actually look at the set of all subsets. There's some very funny subsets that we actually need to throw out. But for the purpose of this class, we're never going to look at those kinds of sets, and it's going to be okay just to think of it as a map from all subsets to 0, 1. So it's not completely formal, but it's functional. Also, you may have forgotten about this notation. So you guys should all have seen series. Everybody's taken calculus too, I believe. And I know that's a little scary to you the first time you see it. You'll get more comfortable as it comes up more and more, so it will be in this class. So you have this symbol from I equals 1 to infinity just means to add up all the numbers, right? P of A1 plus P of A2 plus, and you just plug in these values for I. The union means the same thing. So this, let me use red maybe. So the union from I equals 1 to infinity of AI is just A1 union A2 union A3 and so on. Like that. So instead of putting plus signs in between a bunch of numbers, we have a bunch of sets that are all unioned. And finally, we're putting these numbers in a list. So if A1, A2, A3, and so on are sets such that any two intersected gives the empty set. So notice that none of the sets have any elements in common. Then we can do this. Well, because we put them in order, this kind of implies that these things are countable. So remember that the integers and the natural numbers and the rationals are all countable, but the real numbers are not countable. So you can't do this with like a collection of sets that are indexed by the real numbers or something. It has to be some countable collection. But again, in this class, that's not going to come up too often. However, if you were to take a more advanced class, that would be something important to keep in mind. We haven't really talked in depth enough about infinities, actually, to be really comfortable talking about those things, I believe. We only spend a little time in discrete math doing it. So I don't expect you to be that comfortable with it yet. Once you take real analysis, you'll get a lot more comfortable with the different types of infinities. But let's take those two rules and get a few basic results about probability. So, rule 2, let's take a set A contained in omega. So notice that A is an element of the power set of omega, because this is the set containing every subset of omega. So A belongs to the power set. Then notice that A intersect A complement is the empty set. There's nothing that's both in A and not in A. So remember the intersection is and we can't have some element in X that's in A and not in A. So this intersection is empty. Therefore, the probability of A union A complement is equal to the probability of A plus the probability of A complement. That's by the second rule of the definition of probability. However, if we say all elements that are in A or not in A, that's everything in the universe. Everything is either in A or it's not in A. And therefore, this is also the probability of omega, the entire universe, which is 1. So here, this is by I, the first rule, and the definition, and this is by the second rule. And then this equality follows simply by set theory. So, if we subtract the A over probability of A to the other side, we have 1 minus the probability of A is equal to the probability of A complement. Or P of A plus P of A complement equals 1 is kind of interesting in itself. The probability that A occurs or doesn't occur is 1. And the probability that A doesn't happen is 1 minus the probability that A does happen. I guess similarly, say that B is a subset of A, which is a subset of omega. So everything in B is in A. And these are both in omega, so it makes sense to apply the probability function to B and A. Claim the probability of B has got to be less than or equal to the probability of A. So using our previous knowledge of set theory and just the definition of a probability, we want to show that this is true. So A is equal to B union A intersect B complement. So this we can verify from set theory, which we should know from last semester. We could draw it in a Venn diagram. So we have a set A, and we have a set B. And B is contained in A. So B is a smaller set that's sitting inside of A. And now then if we take everything in B, that would be this part, and we also count everything that's in A and not in B. So here's the stuff that's in A and not in B. So that would be that part. So this is A not in B, and this middle part, of course, is just B. Then we end up getting the entire set A. That gives us all of A. Also, B and A and not B is empty. Because you can't be in B and be not in B and be in A. Because nothing's both in B and not in B. So this is empty. And we again apply rule 2. So the probability of A is equal to the probability of B union A intersect B complement. That's just simply by substitution for this formula. And now then we can apply rule 2. This is the probability of B plus the probability of A intersect B complement. Okay, and remember the probability function takes everything from sets to the interval 0, 1. So in particular, the probability, whatever number this is, A intersect B complement, has to be bigger than or equal to 0. Right, because P is a map from the power set of omega to 0, 1. So the only values it could take is something between 0 and 1. All those values are at least as big as 0. So this is bigger than or equal to, we'll just plug in 0 here, so it's just P of B. Plus 0, which equals P of B. That's what we wanted to show. If you put it all together, we have P of A is bigger than or equal to P of B. In lecture, we'll verify a few more rules. I'll have you guys come and do some at the board probably. We'll also talk about kind of the intuitive meaning, what this means in terms of actual events, and if we were to measure the probability of events. This one, for example, says that every time B occurs, A has to occur as well. And so the probability that A occurs is going to be bigger than the probability B occurs. Yeah, we'll get into that a bit more depth in class. All right, God bless you guys. We'll see you soon.